In this video, I am going to be talking about the ratio test, which is a nice little test for determining convergence, including absolute convergence for alternating series. So the ratio test says that a series with non-zero terms, let rho be equal to the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. All right, so a sub n, of course, is that, and a sub n plus 1 simply means that for every n, we add 1 to it. So you'll see in the examples how that works. And so we have the three different outcomes. If rho is less than 1 but greater than or equal to 0, then the series converges absolutely. If rho is greater than 1 or is equal to infinity, then it diverges. If rho is equal to 1, it doesn't really provide any information whatsoever. All right, so let's get in and see how we use this nice little test. These are one of my favorite tests. So here is our series, and we want to determine, using the ratio test, whether the series converges or diverges. So first of all, I'm just going to put it down here. A sub n is clearly 2 to the n over n factorial. Therefore, a sub n plus 1 is 2 to the n plus 1 over n plus 1 factorial. So wherever we have an n, we add 1 to it. So that's where I get this. All right, so there's my a sub n plus 1, because remember the formula is it's the absolute value of a sub n plus 1 divided by a sub n. So I didn't write it as a complex fraction because that's just took up a lot of room. I just rewrote it as a division problem and then rewrote it as a multiplication problem. And I think some of the problems I just rewrote it as a multiplication problem. So, all right, so this is the original problem, and then rewriting it as a multiplication problem and doing some nifty little factoring here. So first of all, let me get rid of this. 2 to the n plus 1. Let's just explain where that comes from. 2 to the n plus 1 is 2 to the n times 2 to the first. All right, so remember your exponent rules. When you are multiplying bases, you add the exponents. So we're multiplying the bases 2, and when we do that, we simply add the exponents. So the result is 2 to the n plus 1. So all I'm doing is doing this in reverse, breaking that down. And so you're going to do a lot of that with the ratio test. Next is what happened with the n plus 1 factorial. How did that become n plus 1 times n factorial? All right, so remember what a factorial is. A factorial is like if you have 9 factorial, that would be 9 times 8 times 7 times 6, all the way down to times 1. So if you have 9 factorial, you could rewrite this as 9 times 8 factorial, couldn't you? Yes, you could. 9 times 8 factorial would be this exact same thing. Think about it. And so that's what I did here. That's what we did here. If you think of the 9 as being the n plus 1, right? 9 is equal to the n plus 1 in this. 9 is the n plus 1, and then 8 would be n factorial. So we're breaking it down into n plus 1, that would be the 9, times 8 factorial. So think about that. See, make sure that that makes some sense. If that does not make some sense, I can do another video explaining that in a little bit more detail. But that's something else that you're going to see a lot of in these problems. All right, so let's kind of get rid of some of this stuff. All right, so from here, we're doing a lot of factoring and canceling. All right, so n factorial and n factorial cancel. 2 to the n, 2 to the n cancel. And so what are you left with? You're left with a 2 in the numerator and n plus 1 in the denominator. So the absolute value of 2 over n plus 1. Well, we can take the limit of that very easily, and the limit is 0. So because 0 is less than 1, rho then, therefore rho is equal to 0. Rho is equal to 0, which is less than 1. Because of that, the series converges absolutely. Now, this is not an alternating series, but it doesn't matter. It can be used to test for convergence for an alternating series or a non-alternating series. If it is an alternating series, then it is absolute convergence. Next up, so we have this series. And so again, n to the n becomes, every time there's an n, we add 1 to it. So we have to add 1 to the base, n plus 1. And then we have to add 1 to the exponent, n plus 1. And then again, the n factorial in the denominator is just like the last one, n plus 1 factorial. And so that's where we get this from. Divided by the denominator, or times the reciprocal of the denominator. And then I broke n plus 1 to the n plus 1 up into these two terms, just like I explained in the last video. If you have n plus 1 times n plus 1 to the first, and you're multiplying the bases, you have n plus 1 to the n plus 1. And then in the denominator, I did the same thing with the factorial as in the last example. And so from there, it's just a lot of canceling. N factorial cancels with n factorial. The n plus 1's cancel. And so what we're left with then is n plus 1 to the n over n to the n. And so we can combine that as n plus 1 over n, all raised to the n, and that's the absolute value of that. Now, I didn't go through the limit process from this point on because I did that in another video a while back. Of course, I don't expect you to remember it, but what I do expect you to remember is that whenever you have an n plus 1 over m raised to the n power, that is the definition of E. Okay, the limit of that. Okay, and the limit as n approaches infinity. So it would behoove you to remember that. And of course, you may also see that as 1 plus 1 over n to the n. Sometimes that's the more common way of seeing it. The limit of 1 plus n over to the nth power equals E. So that all equals E. E is greater than 1, so the series diverges. And in this last one, this looks a little more complicated. So -1, so this one is an alternating series because we can tell that by the -1 to the n power. So -1 to the n power becomes -1 to the n plus 1 power. N factorial quantity squared becomes n plus 1 factorial quantity squared. Make sure that you get the square, the whole thing, the whole factorial is being squared. 2n, and be careful with this one, 2, we're just adding 1 to the n. It's not 2n plus 1 factorial. It's 2 times the n plus 1, okay, factorial. Okay, so the whole thing, the factorial is of the whole thing, including the 2, but you're only adding 1 to the n. Be careful. This would be wrong. All right, so you're going to end up with this. And then I skipped the division part, just went to multiplication by the reciprocal. And then the next part, I broke that up. Negative 1 to the n plus 1 is negative 1 to the n times negative 1 to the 1. And of course, negative 1 to the 1, and we're doing the absolute value because all of this is within absolute value symbols. So this thing is just going to go away. What else? So the n plus 1 factorial, again, we can factor that into n plus 1 times n factorial. The quantity is being squared. And then the 2 times n plus 1. So to go from here, or to go from this, let me do that in another color. To go from here to here, I did that over here because that may not be overly intuitive. But because of limited space, I want you to think about it. So first of all, this is just algebra going from here to here, distributing the 2. And then 2n plus 2 factorial, well, that would be the same as 2n plus 2 times 2n plus 1 factorial. Or it would be the same as 2n plus 2 times 2n plus 1 times 2n factorial. We're going from plus 2 to plus 1 to plus 0. And so play with it. Let n be equal to a number, and you'll see that this does work, that you can actually write 2n plus 2 factorial in this way. The key here is you're decreasing by 2, 1, and then 0. All right, so we've got all of that down here. Now we can start cross-canceling. So 2n factorial and 2n factorial. We've got n factorial squared, the negative 1 to the n, the negative 1 to the n. And so what we're left with is this n plus 1 squared all over this stuff down here. So here's what we got. All right, and so multiplying all that out, n plus 1, I don't know why I added this extra step. It was kind of unnecessary. But we want to go right down to this step. And so you've got the limit of a rational function. And so you can do this by taking L'Hopital's rule. You can do it a little bit simpler way by dividing everything through by the highest power of n, which is n squared. We have a number of different ways of finding the limit of a rational function. Either way, it's going to come up to 1/4. 1/4 is less than 1, so the series converges. So the new thing that's going to take a little bit of getting used to is how you break up some of this stuff that we're doing in here. Make sure that you understand these connections. Make sure you understand how this stuff is working. And again, if anybody is having difficulties, like I just don't get what you're doing here, I would just be fine with making another little video just kind of going over some of these things. But you got to let me know. All right, so that's it for this video. The next video is going to be on the root test, which is similar but different. Bye-bye.